Hello, everyone, and God bless you. Welcome to this new course on sequences and series. So, this would be mainly a practice, and you can consider it as part of advanced analysis. So, I hope you enjoyed this video. Let's get into it. Now, in this video or session, if you want to call it that, we're going to cover limits of sequences, monotonicity, and boundedness. By the way, a monotone sequence is an either increasing or decreasing sequence. As for boundedness, means that the sequence either have an upper bound or a lower bound. Arithmetic sequences, geometric sequences, infinite geometric series, sigma notation, convergence sets, power series, Taylor and Maclaurin series, and their applications. 1. Determine whether the sequence converges and find the limit. an is equal to 3n plus 5 divided by 2n minus 1. Okay, so limit of an as n approaches infinity is equal to limit of 3n plus 5 divided by 2n minus 1 as n approaches infinity. Let's divide by n both the numerator and the denominator. So it is equal to limit as n approaches infinity of 3n divided by n is 3 plus 5 over n divided by 2n over n is 2 minus 1 over n. Now as n approaches infinity, 5 over n approaches 0. So does 1 over n. So we are left with 3 over 2. Hence, this sequence is convergent and it converges to 3 over 2, which is the limit as n approaches infinity. So here's the solution. You divide the numerator and denominator by n. So an is equal to 3 plus 5 over n divided by 2 minus 1 over n. 5 over n and minus 1 over n both approach 0 as n approaches infinity. Hence, limit an as n approaches infinity is equal to 3 over 2. Therefore, the sequence converges to 3 over 2. Another similar example, find limit as n approaches infinity of 5n squared minus 3 divided by 2n squared plus 1. So it is the limit as n approaches infinity. Also, we divide by n squared both the numerator and the denominator of 5. n squared divided by n squared is 5 minus 3 over n squared divided by 2 plus 1 over n squared. As n approaches infinity, these two approach 0, so the limit is equal to 5 over 2. Hence, this sequence converges, and its limit is 5 over 2, so it converges to this number. And here's the solution. You divide by n squared, both numerator and the denominator. The limit of these two, which is 3 over n squared and 1 over n squared, is 0 as n approaches infinity. So therefore, the limit is 5 over 2, which is also the point of convergence of the function as n approaches infinity. 3. Determine whether an is equal to minus 1 to the power of n divided by n converges. Now, as n keeps switching from an odd to an even number, because as n increases, it's at times equal to 1, then equal 2, then equal 3, then equal 4. If you notice, it keeps flapping between an odd number and an even number. Whenever n is odd, an would be equal to minus 1 over n. When n is even, then minus 1 becomes plus 1. Okay? 4. This is for n odd. And here, for n even, an is equal to plus 1 over n. So it keeps switching from a negative value to a positive value. Now here we're going to introduce what is called the squeeze theorem. You see, an, therefore, is greater than or equal to minus 1 over n, less than or equal to plus 1 over n. It is between these two values. So the squeeze theorem postulates the following, that since minus 1 over n approaches 0 here in this case as n approaches infinity, the same way that plus 1 over n approaches 0 as n approaches infinity, and having an between these two bounds, so an given the fact that it is greater than equal to minus 1 over n, less than or equal to plus 1 over n, hence, since an is squeezed between these two limits and both approach 0, therefore an also approaches 0 as n approaches infinity. So here's the solution. An being between minus 1 over n and plus 1 over n, and both bounds approach 0, therefore the limit of an as n approaches infinity is equal to 0. Determine whether an equal to minus 1 to the power of n converges. Now, just like we've seen before, for n having an odd value, such as n equal 1, 3, 5, 7, an is equal to minus 1 for an odd power. But for n having an even value, such as 2, 4, 6, 8, etc., then in such case an would be equal to plus 1. Since an keeps oscillating between minus 1 and plus 1, never reaching a fixed value, hence this sequence does not converge. Actually, it is the exact opposite. It diverges given the fact that it never stabilizes on a fixed value. It keeps going up and down between minus 1 and plus 1. So it diverges. Here's the solution. The sequence alternates, this was the word I was looking for, between plus 1 when n is even and minus 1 when n is odd. So an keeps going back and forth between minus 1 and plus 1, and these are the different values, like always flapping between minus 1, plus 1, minus 1, plus 1. Therefore, since there is no single value that is approached, so the function is divergent. Limit as n approaches infinity of nth root of 5. Okay, so how to solve that? Let's rewrite it as limit as n approaches infinity. Nth root of 5 is actually 5. It can be written this way. 5 to the power of 1 over n. Now, as n approaches infinity, we know that 1 over n approaches 0. So this power over here becomes 0. Okay, so limit of 5 to the power of 1 over n as n approaches infinity is equal to 5 to the power of 0, which is equal to 1, because anything to the power of 0 is equal to 1. So, for any positive constant c, limit as n approaches infinity of c to the power of 1 over n is equal to 1. Hence, the limit is equal to 1, and we just explained why. 6. Determine whether the sequence an is equal to ln n converges. Now we know that as n approaches infinity, ln infinity also blows up. ln n blows up to infinity. So this sequence definitely diverges. So ln n approaches infinity as n increases to infinity, and it is a divergent sequence. 7. Determine whether an is equal to 1 plus 1 over n to the power of n converges. Here, as a reminder, in one of the laws of the exponential, or one of the identities, so to speak, when you have a quantity which is 1 plus u, for example, to the power of 1 over u, so 1 plus something to the power of 1 over something, which is the inverse of that something, this is equal to e, the exponential. Therefore, limit an as n approaches infinity equal limit 1 plus 1 over n to the power of n as n approaches infinity. And you notice here, you have in the power the inverse of that number on the inside, which is 1 over n. The power is the inverse, which is n. Therefore, this is equal to e, or the exponential. So the limit converges to number e. Here's the solution. Limit 1 plus 1 over n to the power of n is equal to e. 8 show that an is equal to n divided by n plus 1 is increasing. Now, the test that we have to run is checking whether an plus 1 minus an is greater than 0. Because in such case, when you have an plus 1 minus an, or in other words, the next term minus the previous term is greater than 0, then you can conclude that the sequence is increasing. So to give you an example, let's say you have a sequence of 1 plus 2 plus 3 plus 4. How can you know? Okay, here it should be clear that it is increasing. But to prove the point to you, okay, so let's say we want to prove that this sequence is increasing. So we take a second term, or like a consequent term, we subtract it by a previous term of that sequence, and the value should be positive, greater than 0. So let's say this is a0, this is a1, this is a2. Okay, so a2 minus a1 is equal to, for example, 3 minus 2 equal to 1, greater than 0. Hence, this sequence is indeed increasing. And by the way, the definition of a monotone sequence, it would be increasing and bounded. Okay? Monotonic means increasing or decreasing, by the way. It's either increasing or strictly increasing or strictly decreasing and having an upper and lower bound. So, let's check for an. An plus 1 is equal, so we are trying to apply this formula. An plus 1 minus an should be greater than 0 to prove that it is increasing. An plus 1 is equal to, we simply replace n by n plus 1. So it is n plus 1 divided by n plus 1 plus 1, or n plus 2 in the denominator, minus an, which is minus n divided by n plus 1, is equal to n plus 1 over n plus 2 minus n divided by n plus 1 equal, let's take a common denominator, n plus 2 times n plus 1. Okay, so we multiply to the left by n plus 1, so we end up with n plus 1 squared minus n times n plus 2 equal to, let's remove, okay, so n plus 1 squared is equal n2 plus 2n plus 1 minus, I'm developing this side, n squared minus 2n divided by n plus 2 times n plus 1. So n squared minus n squared is eliminated, minus 2n plus 2n eliminated. So this is equal to 1 divided by n plus 2 times n plus 1. For whatever value of n, it is greater than 0. So as n increases, this value decreases, but it remains greater than 0. Hence, this sequence is increasing. You can say that it is monotonically increasing. So an plus 1 minus an is equal to n plus 1 divided by n plus 2 minus n divided by n plus 1, which is 1 over n plus 1 times n plus 2, and it is greater than 0. Hence, the sequence is increasing or monotonically increasing. Determine whether an is equal to 1 over n is bounded. Okay, now, first of all, this sequence has a maximum. What is the maximum? We know that n starts increasing from 1 all the way to infinity. So the maximum that this sequence would have is when n is equal to 1. So an equal 1, that would be the upper bound or the maximum, the highest value that an can get or can get to. And by the way, it is included within the set, so it is part of the interval. It's not excluded. As for the lower bound, now, limit of 1 over n as n approaches infinity is equal to 0. Hence, the lower bound is 0. So, an exists within the interval starting from 0, but 0 is excluded, up to 1, but 1 is included. Actually, by the way, another annotation on how you can write it, this is 0, and to indicate that it is excluded, you open the square bracket sideways. As for 1, it is included within the interval, so you close the set on it, so the bracket would be opened inward. Let's check the solution. So an is greater than 0, strictly less than or equal to 1. Thus, the sequence is bounded above and below. Exactly. Another way to write it is an strictly greater than 0, but less than or equal to 1, which is another way of saying an exists within this interval, which is open at 0, but closed at 1. So 1 is part of the values accepted at an, or that an can have. Use the monotone convergence theorem to show that an is equal to 1 minus 1 over n converges. What does it mean? When a sequence is monotone, so whether monotonically increasing or decreasing, and when it's also bounded, so it needs to fulfill these two criteria or conditions. It should be monotone or monotonically increasing or decreasing and also bounded. Hence, you can deduce that the sequence is convergent. So let's check it out. At first, for an to be monotonically increasing, an plus 1 minus an should be greater than 0. Let's check it out. So an plus 1 is simply obtained by replacing n by n plus 1. So 1 minus 1 over n plus 1 minus an, which is 1 minus 1 over n, is equal to 1 minus 1 over n plus 1 minus 1 plus 1 over n equal, okay, 1 minus 1 is 0, so you end up with 1 over n minus 1 over n plus 1. Now, 1 over n plus 1 is less than 1 over n, correct? So 1 divided by n plus 1 is less than 1 over n. Hence, 1 over n minus 1 over n plus 1 remains greater than 0. So this sequence is monotonically increasing. As for the limit, let's find the limit. To to check whether it's bounded or not. That's why we are looking for the limit. Limit an as n approaches infinity is equal to limit 1 minus 1 over n as n approaches infinity. This part cancels out, becomes 0, so the limit becomes 1. Given the fact that this sequence is bounded, and also given that it is monotonically increasing, so it converges. And here's the solution. The sequence, again, is increasing monotonically, as we checked through the test, the comparison test of an plus 1 minus an, which should be greater than 0. And it was proven that it is greater than 0, so it is monotonically increasing. Plus, it is bounded above by 1, because the limit as n approaches infinity is equal to 1. By the way, speaking of which, the minimum for this sequence to have is 0. So for n is equal to 1, an would be equal to, or a1 in such case, would be equal to 1 minus 1 equals 0. So this is the lower bound, the minimum. As for the maximum, is obtained as n approaches infinity. So minus 1 over n approaches 0. Now it would never exactly become equal to 0, but it approaches 0. So the upper bound, or the highest maximum, the highest value that the function can reach, but it never reaches due to the fact that 1 over n approaches 0 but never gets to 0. So the upper bound is 1. So an exists between 0, greater than or equal to 0, less than 1, never becomes equal to 1. It is bounded above by 1, and also it is monotonically increasing. Therefore, it converges and the limit is 1. Part 2, arithmetic sequences. 11. Find the 20th term of 2, 5, 8, 11. Okay, all the way. Now, there's a formula for the arithmetic sequences, but let's say, just in my case, I had forgotten the formula for that, okay? So how can we figure out the 20th term? If you notice something by looking at the sequence, we see that there's a gap of 3, okay, which is the increment between each two consecutive numbers. So between 2 and 5, you have 3, which is 2 plus 3 equal 5. Between 5 and 8, also 5 plus 3 equal 8. 8 plus 3 equal 11. So how can we compute the 20th term? If we take 2 and 8, for example, how many steps are there from 2 to reach 8? You have first step and second step. So 2 steps multiplied by the gap, which is 3. This is 6, right? And we add these 6 gaps to the original number, which is the first term here, which is 2, equal to 8. So the 20th term, starting now, the 20th term includes the 2 at the beginning, okay? So the 20th term would be the 19th, okay, so it would be 19 multiplied by the gap, which is 3, plus the original term, which is 2, okay? So 2 plus 19 steps, okay, it is the 19th term, so the 19th jump, because plus the first one is equal to 20, multiplied by the gap, which is 3. Hence, it is, okay, 3 times 9, 27, 7, 2, okay, 3 times 1, 3 plus 2, 57, plus this 2 over here, which is the original term, is equal to 59, if I'm not mistaken. Let's check it out. Now, the formula is an is equal to a1, the first term, plus n minus 1 times d, which is exactly what we did, by the way. So it is the first term plus 20th term, so you compute 20 minus 1, which is the 19th after the first one, multiplied by d, which is the distance gap of 3, plus the first term, which is 2. Okay, so a1 equal to the distance or the gap is equal to 3. So 820 is equal to plus 19 times 3 equal 59. Another similar exercise, find the sum of the 50 terms. Okay, so an is equal to a1, the first term, plus n minus 1 times d. What is the distance between two consecutive terms, any two consecutive terms? It is equal to 3. 3 plus 1, 4, 4 plus 3, 7. As for the 50th term, so 50 minus 1, 49. So it is equal to a1, which is 1, plus the first 50 terms, so it is 50 minus 1, 49, multiplied by the gap, which is 3, equal 1 plus 3 times 9, 27, 7, 2, 3 times 4, 12, plus 2, 147, plus 1, 148. Let's check it out. So this is the answer, 148. Now, notice something what he exactly asked. He did not say, give me the 50th term. Give me the sum of the first 50 terms. So we need to add them all up. So 148 is the value of the 50th term, meaning the term number 50 is 148, exactly as we computed. However, he wants the sum of all the terms starting from the first one all the way to the 148, which is the term number 50. So how do we get that? S50 is equal to 50, so it is 50 terms, right? Divided by 2, multiplied by 1 plus 148. It is part of the sequence theorems, by the way, which is 3725. This is the sum. Again, for the sum of the n terms or for the sequence up to the nth term, which is different than finding the nth term, this is adding up all terms up to n. So in such case, the formula would be n, which is the number of terms, multiplied by the value of the nth term, which is a1, first term, plus n minus 1, with n being 50, multiplied by 3, which is the distance between the terms. Given that we don't have any values missing, so it would be 50 multiplied by 1 plus n minus 1, which is 49 multiplied by 3. But in this case, you have half of the values missing, because if you notice, you have 1 plus 2 plus 3 plus then 4. Okay, 2 and 3 are missing. Plus 5 plus 6 plus 7. So half of the values are missing. Hence, the sum is equal in such case 50 over 2, which is half of the values available, multiplied by 1 plus 49 times 3, 3725. By the way, here the value should be 147. I think there's a mistake because 3 times 49 is 7, then 2, 3 times 4, 12, so 147. Plus 1, 148, times 50 over 2, so that would be, okay, 50 times 148 over 2. Let's divide 148 by 2. So it is 74 times 50 equal 0, 5 times 0, 4, 20, 0, 2, okay, 35. So it is 3700, not 3725. That should be the correct answer. 13, find the common difference if a1 equals 7 and a15 equals 63. We simply apply the formula that we already know. So a15 is equal to a1 plus n minus 1 times d, and the distance is the one that, or the difference is the one that we are looking for. So n is 15. Hence, a15, which is 63, is equal to a1, 7, plus 15 minus 1, 14d. So 14d is equal to 63 minus 7. That would be 60 minus 4 or 56. So d is equal to 56 divided by 14. Okay, so 4 times 4 is 16, 6, 1. 4 times 1, 4 plus 1, 5, 56. Hence, the distance or the difference is equal to 4. And here's the solution. 63 equal to 7 plus 14d, and d equal to 4. Part 3, geometric sequences. 14. Find the tens term for 3, 6, 12, 24. Now, for a geometric sequence, the formula is an for an nth term is equal to a1 times r to the power of n minus 1. If we look at the gap between different elements in this sequence, so the first gap is 3, because 3 plus 3 equals 6. Then the second one is 6, because 6 plus 6 equals 12. Then 12. So we notice something that it is actually doubling. Okay, so what is the reason, or R? Let's examine the terms between 3 and 12. So 3 is the first term, a1, right? 12 is 1, 2, okay, it is the third term. So a3 is equal to a1 times r to the power of n minus 1, right? N being 3 in such case, minus 1, so r squared. a3 is equal to a1 times r squared. So r squared is equal to a3 divided by a1 equal a3 is 12, the third term, divided by a1, the first term. 12 over 3 equal 4. So what is r? R squared equal 4. Therefore, r is equal to plus 2. Let's try it for the term 24. 24 is the fourth term. So a4 should be equal to first term a1 times r to the power of n minus 1 equal a1 3 times r2 to the power of n minus 1, which is the fourth term, minus 1, or 3, which is 8. 2 to the power of 3 is 8, multiplied by 3 equal 24, which is correct. Hence, the tens term is given by a10 equal to a1 times r to the power of n minus 1, which is 3 times 2 to the power of n minus 1. What is n? 10. Minus 1 is 9. So it is equal 2 to the power of 8, 64, right? Actually, no. 2 to the power of 5 is 32. To the power of 6, 64, 7, 128. To the power of 8, 256. Then times 2. You can actually evaluate it using a calculator. 2 times 6, 12, 2, 1, 2, 5, 10. So 10 plus 1, 11, 1, 1, 2, 2, 4. Okay, 5 12s, 5 12 times 3. Equal 6, 3, and 15, or 1, 5, 3, 6. And this is correct. So the an term, or the anth term for n equal 10 is equal to 3 multiplied by 2 to the power of 10 minus 1, which is 9, equal 1536. Find the sum of the first 8 terms for this following example. At first, what is r in such case? Going back to the formula that we know, an is equal to a1 times r to the power of n minus 1. So let's take 6 and 2 for example. So 6 is a2, the second term is equal to a1, the first term which is 2, times r to the power of n minus 1, where n equal to minus 1, so it is r to the power of 1, or simply r. Hence, r is equal to a2 divided by a1, which is 6 divided by 2, equal 3, so r is equal to 3. As for the sum in the geometric sequence, it has the following formula. Sn is equal to a, which is the first term. Here a is equal to 2, and r equal to 3. We just found r moments ago. So Sn is equal to a times r to the power of n, which is the nth term, minus 1 divided by r minus 1. This is how we get the sum up to the nth element in the sequence. So Sn is equal to a times r to the power of n minus 1 divided by r minus 1, where n is the nth term up to which we are evaluating the sum. So we know already that the first term, which is a, is equal to, and r, which is the recurrence, is equal to 3. So Sn is equal to a times r to the power of n minus 1 divided by r minus 1, which is equal to multiplied by 3 to the power of 8 minus 1 divided by r minus 1, which is 3 minus 1, or 2, equals 6560. 16, determine whether an is equal to 5 multiplied by 1 over 3 to the power of n converges. Here's the rule. Let's say you have an, a sequence equal to a multiplied by p, let's say, to the power of n. Now, if p is less than 1, then an converges definitely. So here what we have is 1 over 3. In absolute value, it is less than 1, meaning that as n approaches infinity, this quotient, which is 1 over 3, decays all the way to 0. So as n approaches infinity, 1 over 3 tends to 0. Therefore, the entire product here, which is 1 over 3 to the power of n times 5, also approaches 0. So the entire sequence decays to 0. Therefore, this an sequence converges to 0. So 1 over 3, an absolute value, is less than 1. Limit an as n approaches infinity is equal to 0. So therefore, it converges to 0. Infinite series. Determine whether sigma n equal 1 to infinity of 1 over n converges. Okay, now, this is the rule for such series. When you have 1 over n to the power of p, and p is greater than 1, then the series converges. Otherwise, it diverges. Here you have p is equal to 1. So this series never converges, it is divergent. And by the way, it is part of the harmonic series, so it is divergent. Also, of course, based on what we presented before, with p being the power of n equal to 1 instead of being greater than 1, which is the criteria or the condition for it to converge. 18, determine whether sigma 1 over n squared converges. Of course, from n equal 1 to infinity. So here, in this case, you have 1 over n to the power of p, where p is greater than 1. So the entire series decays to 0 and converges as n approaches infinity, given the fact that the power is greater than 1. Now it is a different thing than when we're talking about sequences. Series are a little bit different, because you would think, okay, but as n approaches infinity, this should definitely decay, which is not the case, because you are adding up values. This is the difference. It is not 1 over n we are testing. It is the series of 1 over n from n equal 1 all the way, and we are adding up these values. So you have, let's say if n is equal to, or rather if p is equal to 1. So 1 over 2, right? Plus 1 over 3 plus 1 over 4 if p, the power is equal to 1. So it diverges, it keeps going. It is a harmonic repetitive series. Meanwhile, for n squared, what you would get is 1 over 2 squared, which is 4, plus 1 over 9, plus 1 over 4 squared is 16. So it decays rapidly all the way to 0. This is the missing part. This is the difference between a series and a sequence. So for p greater than 1, the series converges. Again, this is called a p-series technically, with p equal to greater than 1. Therefore, it converges. 19. Find sigma n equals 0 to infinity of 1 over 4 to the power of n. This series can be rewritten as 1 divided by 1 minus 1 over 4, which is equal to 1 divided by, 4 minus 1, 3 over 4, or 4 over 3. So it converges to this value. It is, again, a type of an infinite geometric series with s equal 1 divided by 1 minus 1 over 4 equal 4 over 3. Determine the convergence, this is 20, of sigma n equal 1 to infinity of 1 over n to the power of 3. Now, it is a p-series of type 1 over n to the power of p, and p is greater than 1, so it converges. Given that p is equal to 3, which is greater than 1, therefore it is convergent. Determine the convergence for sigma n equal 1 to infinity of 1 divided by square root of n. Okay, so square root of n can be rewritten as 1 divided by n to the power of 1 half. So p here, because it is a type of p series, p is less than 1, therefore it is divergent. Here's the solution. At times when you have complex functions or series rather, it is hard to determine the convergence based on the basic shapes of a p series or something like that. So we need to perform either of two typical tests to determine the convergence or divergence, which are the ratio and root tests. Starting with sigma n equal 1 to infinity of n divided by 2 to the power of n. To run the ratio test, we simply divide an plus 1 over an, and if this quotient is less than 1, it means that the series converges. Why? Because it keeps decreasing and decaying to a finite value. Meanwhile, if it is greater than or equal to 1, it diverges. Why? Because it either keeps increasing or it keeps a specific, it keeps the same pattern of development. It has a constant, steady rate. So an plus 1 divided by an is given by, you simply replace n by n plus 1. So it is n plus 1 over 2 to the power of n plus 1 divided by n divided by 2 to the power of n equal. This is n plus 1 over 2 to the power of n plus 1, by the way, can be written as 2 to the power of n multiplied by 2. And let's flip the denominator and multiply here, times 2 to the power of n divided by n. Now, 2 to the power of n, factor out in the numerator and the denominator, we are left with n plus 1 divided by 2n. So what is the limit as n approaches infinity? Limit as n approaches infinity of n plus 1 divided by 2n is equal to, we divide by n both in the numerator and the denominator, so it is 1 plus 1 over n divided by 2. As n approaches infinity, 1 over n approaches 0, and you are left with 1 over 2, which is a value less than 1. Therefore, this series converges. And here's the ratio test again. L is equal to the limit as n approaches infinity of n plus 1 divided by 2 to the power of n plus 1 over n divided by 2 to the power of n, which is equal to 1 half. The limit is less than 1, therefore the series converges. 23 sigma n equal 1 to infinity of n factorial divided by n to the power of n. Let's find out whether it converges using also the ratio test. So it is the limit as n approaches infinity of n factorial becomes n plus 1 factorial divided by n plus 1 to the power of n plus 1 over n factorial divided by n to the power of n equal. Now, by the way, n plus 1 factorial is equal to n times n factorial. I prove it to you. It is like saying 5 plus 1 factorial. It is 6 times 5 factorial, correct? Because it is 6 factorial, which is 6 times 5 factorial. So, n times n factorial divided by n plus 1 to the power of n plus 1 means n plus 1 to the power of n multiplied by n plus 1. Then let's flip the quotient here and multiply times n to the power of n divided by n factorial. Now n factorial can be removed, so it is equal to limit as n approaches infinity of n times n to the power of n divided by n plus 1 to the power of n multiplied by n plus 1 equal. So also in the numerator you have n times or to the power of n plus 1 divided by n plus 1 to the power of n times n plus 1. Let's break it down. So it is the limit as n approaches infinity of n divided by n plus 1 multiplied by n to the power of n divided by n plus 1 to the power of n. Now, as n approaches infinity, you have the first part. Okay, so if we divide by n, you get 1, correct? So n over n, here n over n plus 1 over n. So this becomes 0 and n over n, the numerator and the denominator become 1. So the relevant part is the one to the right. As n approaches infinity, okay, you have n to the power of n in the numerator, but also in the denominator n plus 1 to the power of n. Now, n plus 1 is greater than n. As n approaches infinity, the denominator becomes larger than the numerator. Therefore, this quotient decays to 0. And by the way, it can be rewritten as limit as n approaches infinity of n divided by n plus 1 to the power of n. As n approaches infinity, this entire quotient approaches 0. To the power of n, it decays even more quickly, given that this value here is less than 1. That's why. So anything less than 1 raised to the power of n decays to 0. So here's the result of ratio test. So it is the limit of n divided by n plus 1 to the power of n, which is, by the way, is equal to exponential of minus 1. Because remember the formula, 1 plus something to the power of 1 over something becomes e, exponential. So what do we have here? You have, okay, so n divided by n plus 1 can be 1 plus 1 divided by n. It becomes n plus 1 over n. So, and raised to the power of n would be the exponential. Given that this is flipped over, meaning that you have n in the numerator, so instead of n plus 1 over n, you have n over n plus 1. So that would be equivalent to e minus 1, which is 1 over e, the inverse of the exponential. Therefore, again, the series converges. Alternating series. 24. Determine convergence, sigma, n equal 1 to infinity, minus 1 to the power of n plus 1 divided by n. So here we have a type of alternating series where minus 1 keeps alternating between minus 1 and plus 1 for respectively n plus 1 being odd and being even. So if n plus 1 is odd, minus 1 to the power of n plus 1 would be, for example, minus 1 to the power of 3. So remains minus 1. But for n plus 1 being even, it would be like minus 1 to the power of 2. So it becomes plus 1. So it is an alternating series, and as n approaches infinity, positive terms and negative terms cancel each other. Therefore, it is convergent. So notice something, that the terms decrease to 0, and the alternating series test applies. Therefore, it is convergent. But again, what is the alternating series test? I felt that I should get back here to clarify some things. First, we should have that an plus 1 minus an should be less than 0, meaning that as we advance, the term is decaying. So an plus 1 would be minus 1 to the power of n plus 1, let's say, okay, in absolute value. It is less correct than a or 1 divided by n, okay? So 1 over n plus 1 minus 1 over n is equal to n minus 1 divided by n plus 1. So equal to minus 1 over n plus 1, which is less than 0. Therefore, the series is decaying. It is decreasing. Plus limit of 1 over n as n approaches infinity is equal to 0. So both conditions have been met and the series is convergent. Okay, determine whether sigma n equal 1 to infinity minus 1 to the power of n converges. Here we have an alternating series that keeps flapping between minus 1 and plus 1. So for n odd, it is minus 1. For n even, it is plus 1. And it never changes, meaning that it keeps going back and forth between these two values. So never fixates on a value. Therefore, it is divergent. In other words, the terms do not approach 0, and this is why it causes the divergence of this series. Find the radius of convergence for sigma n equals 0 to infinity xn. Let's apply the ratio test. So xn plus 1 divided by xn is equal to xn times x over xn, which is x. Therefore, the radius of convergence is x. In other words, the radius depends on x. So for x less than 1, this series converges. The radius, therefore, is equal to 1. Find the interval of convergence for sigma n equal 1 to infinity, x to the power of n divided by n. Okay. So, again, using the ratio test, it is limit as n approaches infinity of an plus 1 divided by an equal xn plus 1 over n plus 1 divided by xn over n equal xn plus 1 over n plus 1 times n over xn. So it is limit as n approaches infinity xn times x times n divided by n plus 1 times x to the power of n. xn and xn checks out here, so it is equal to x multiplied by n divided by n plus 1. In such case, x should be less than 1. So actually the entire product here should be less than 1. xn less over n plus 1 less than 0, in other words. So xn less than n plus 1, xn minus n less than 1. So x less than 1 based on the test, x should be less than 1. Hence, the ratio test gives x in absolute value is less than 1. Checking the endpoints, so for x equal 1, it diverges. Harmonic series diverges for x equal 1, but for x is equal to minus 1, it converges. So the interval of convergence is from minus 1 being included, all the way to 1, but 1 is not included. Find the Maclaurin series of Ex. So Maclaurin series is given by sigma, okay, x to the power of n over n factorial. Let's check it out. Yeah, Ex is equal to sigma n equals 0 to infinity xn over n factorial, which is 1 plus x over 1 factorial plus x squared divided by 2 factorial plus x3 over 3 factorial. This is how we develop it all the way. Find the first 4 non-zero terms of sine x. So it is equal to x minus x3 divided by 3 factorial plus x5 divided by 5 factorial minus x7 divided by 7 factorial all the way. By the way, the formula is sine x is equal to x times f0 of x divided by 0 factorial. Okay? Then plus x squared times f1 of x, meaning the first derivative, divided by 2 factorial. But the first derivative actually here is, yeah, not the first derivative, sine x. So the first derivative is over here. Okay, it is equal to cosine. Cosine 0 is 1 multiplied by x. But here you get sine 0. Okay, the derivative of cosine is sine. Then, okay, so sine 0 is equal to 0 multiplied by x squared divided by 2 factorial is equal to 0. Then, derivative of sine is cosine. Okay, so minus x3 times f third, the third derivative of the function, divided by 3 factorial, the third derivative, so sine to cosine, then cosine to minus sine, then minus sine to minus cosine. This is the third derivative. Okay? Minus cosine 0 is minus 1 multiplied by x3 divided by 3 factorial. Now, for x4, cosine becomes sine. Sine 0 is equal to 0. Okay? For x5, it becomes minus cosine, minus sine. The derivative, or actually minus cosine, yeah, minus becomes plus, okay, due to the alternation of the derivatives. So it becomes plus x5 divided by 5 factorial, given that you have cosine 0 here, etc. Using the first 4 Maclaurin terms, approximate E0.1. This is approximately equal to 1 plus 0.1 plus 0.1 squared divided by 2. You replace x by 0.1 plus 0.1 to the power of 3 divided by 6, which is approximately 1.10, 51, 67. Evaluate sigma n equal 1 to infinity of 1 divided by n times n plus 1. Now, can we break down this quotient? Okay, here's the thing. 1 over n times n plus 1, you place it equal to a divided by n plus b divided by n plus 1, where a and b need to be determined. So, let's develop it equal to a times n plus 1 over n plus bn over n plus 1. And here you have again a multiplication in the denominator. So 1 over n times n plus 1 is equal to an plus a plus bn divided by n times n plus 1. Okay, so let's equate similar terms next to each other. So a is equal to 1 because you don't have n to the left. Constants are equal to constants and variables equal to variables. A equal to 1 and an plus bn is equal to 0 because n is equal to 0 to the left. So a plus b equals 0. Therefore, b is equal to minus a, which is minus 1. So this term becomes 1 over n, this is a, minus 1 over n plus 1 because b is equal to minus 1. This is, by the way, called telescoping series because the terms keep annihilating each other, one after the other, and you are left with 1. Let's check it out. So 1 over n times n plus 1 is equal to 1 over n minus 1 over n plus 1, correct? Plus 1 over n plus 1 minus 1 over... You keep going. As n approaches infinity, the series telescopes and the limit is equal to 1. The sum is equal to 1. Evaluate the series sigma of 1 divided by 2 to the power of n from n equal 1 to infinity. This can be rewritten as 1 half divided by 1 minus 1 half, where 1 half is the first term. It is simply a1. a1 is equal to 1 half. So it's equal to 1 half divided by 1 half equal to 1. Show that sigma of 1 over n factorial is equal to e minus 1. So how do we go about it? Using e is equal to sigma from n equals 0 to infinity of 1 divided by n factorial, which is the Maclaurin development. Subtract the n equals 0 term. So instead of n equal 1, it becomes from n equals 0. Why? Because it has become 1 plus 1 over n factorial as you move the 1 from right to the left. So e is equal to sigma from n equals 0 to infinity of 1 over n factorial. Therefore, sigma of 1 from 1 to infinity of 1 over n factorial is equal to e minus 1. Let's check the convergence for sigma of 1 over n times ln n from 2 up to infinity. So let's check it out using the integral formula. It is the integral from 2 to infinity of 1 divided by n ln. Can be actually rewritten as integral from 2 to infinity of dx divided by x ln x, which is equal to the limit as t approaches infinity of integral from 2 towards t of dx over x ln x. So let's suppose that u is equal to ln x. du is equal to 1 over x dx, which is this part, right, from the numerator and the denominator. Let's switch the variables. So it is the limit as t approaches infinity of integral from 2 to t. I'm not going to change them immediately here. Of dx over x ln x. Let u be equal to ln x. du is equal to 1 over x dx, which you see obviously in this equation. So therefore, it is the integral from du over u, which is equal to ln u between the bounds presented here, between t and 2, but we need to retrieve back the values of, or the value of ln u, right? So ln u is ln x, correct? Or u is ln x. Therefore, it is equal to ln of ln x between t and 2. It is the limit, therefore, as t approaches infinity. So it is equal to ln of ln t minus ln of ln2, which is a finite value. Now, as t approaches infinity, ln t blows up to infinity, and ln t also blows up to infinity. Therefore, this series diverges. Again, another reminder is that we can use the integration test to check the convergence of a series. So here we check the integral from 2 up to infinity of dx divided by x ln x, and it diverges, hence the series diverges. A similar example, sigma n equal 1 to infinity of 1 divided by n ln n squared. Using the integration test, so integral from 1 to infinity of dx divided by x times ln x squared. Let u be equal to ln x, du equal to 1 over x dx. So this can resolve into integral from 1 to infinity of du over u squared equal to u to the power of minus 2 plus 1 divided by minus 2 plus 1. So 1 over u and minus 1 over u. And by the way, this integral can be transformed into the limit as t approaches infinity of integral between 1 and t of du over u squared. So it is minus 1 over n between t and 1. Actually, no. Minus 1 over u. Okay, so we need to convert. Okay, so u is equal to ln x, correct? So for x equal t, u is equal to ln t. So this u here, this like boundary becomes ln t. For x equal 1, u is equal to 0. So it is between ln t and 0. You need to change the boundaries also. So it's equal to minus 1 over ln t minus 1 over 0. Okay? Which is plus 1 over 0. 1 over 0 blows up to infinity. Minus 1 over ln t. So as t approaches infinity, this becomes 0. So it is supposed to be divergent. As the final summary, a convergent series requires a n approaching 0. Geometric series converges when r, an absolute value, is less than 1. P series converges if p is greater than 1, that is the p series, which is the power in the denominator. Ratio test is useful for factorials and exponentials. Alternating series test requires decreasing terms approaching 0. Power series have a radius and interval of convergence. And Taylor series or Maclaurin series, which is almost the same thing, approximate functions using polynomials. Thank you so much for watching and see you next time. Bye bye.